Hey guys, in this video we're going to discuss a two-sample t-test hypothesis test. So the anterior cruciate ligament, or the ACL, is one of the ligaments that helps stabilize the knees. So now we're going to go through this really quickly. I hope everyone read it already, but basically you need surgery and there's going to be recovery time. So a medical center developed a new surgical procedure to reduce the average recovery time for the surgery. To test the effectiveness of the new procedure, they took 210 patients and they randomly assigned to receive either the standard procedure or the new procedure. Based on the design, would a statistically significant result allow the medical center to conclude that the new procedure causes a reduction? Explain your answer. And then it goes on to, do the data provide statistical evidence that those who receive the new procedure will have less recovery time from the surgery on average than those with the standard procedure? So let's just do this part because that's what this video is about. So it's a hypothesis test. There's two samples. We should probably see what the values are. So they took 210 patients. Those are not random patients, but they were randomly assigned 110 and 100. The recovery time was 217 days with 34 days as the standard deviation and 186 days with 29 as the standard deviation. Now, this is going to be a T. Even though these numbers are really high, okay, the S, or the standard deviation, came from this sample. So the standard deviation is unknown, so it must be a T, okay? Also, this is an average problem and not a proportion problem. So HO would be, hey, the two recovery times that make no difference whether you take the standard or the new procedure. Or, now it depends on what you call mu1 and mu2. I'm going to say greater than, where mu1 in this case represents the mean recovery time among all patients, similar to those if they took the standard treatment, and mu2 is the new treatment. Remember, the standard treatment has to be more than the new treatment. So that's step one. Step two is our conditions. And we know there's two conditions. Once again, these 210 patients were not random patients, but they were randomly assigned to one of the two groups. Now, how are we going to show that it's approximately normal? Well, there's a few ways of showing normality. One is the problem can tell you it is. Two is a graphical display. The third way, which we're going to use now, is that both of these ends are bigger than 30. So by the central limit theorem, we can assume that it's approximately normal. So conditions. Because this is an experiment, the first condition is that the subjects were randomly assigned to one of two groups. In this case, the condition is satisfied because we were told the subjects were randomly assigned. The second condition is that the recovery time of the two populations are normally distributed. And what we notice here is that they state what the conditions are and then they show how it's satisfied. So it's satisfied because of 110 and 100. Okay, so that was good. Step three is our formula. We know our formula is statistics minus parameter over the standard deviation of the statistic. This is a two-sample. You can use your formula sheet. So remember that this is our formula. Okay. Typically, we put mu1 minus mu2, but because we're assuming the null hypothesis is equal to 0, this part is not necessary. So this is our formula. When you get to statistics, it's going to either be one sample or two samples. We're going to choose two sample. Then when you read two sample for statistic, it's going to say difference of sample mean or difference of sample proportion. We do means. Then you look to the right of it. This comes with it. But it has sigma, but you're going to have to exchange sigma for S. So that's that. You have to write in all of your values, okay? And after you write in all your values, we come to our calculator. Let's take a look. We're going to press stat, test, two sample, t-test, 217, 34, 110. 186, 29, 100. Greater than, is it pooled? No, it's not pooled. Pooled means that you know that the standard deviations are going to be equal. Okay, so no, it's not pooled. After you press enter, you notice that mu1 is greater than mu2, and you notice that this is positive. Now, I have to be honest, I thought I made an error. Typically, we get nice t values, something along between like negative 3.5 and positive 3.5, but this is 7. It's huge. It's all the way off of the curve. I went back and I checked my numbers. They were all correct. So this is your answer. P-value is 8.35, and you have to say to yourself, P is probability. It cannot be greater than 1. So let me take a look at the end. E to the negative 12 says times 10 to the negative 12, okay? So please be careful, and let's see how we write the p-value, which is step 4. The p-value is this guy. The probability of t being greater than 7.127 is basically 0. Conclusion: assuming that assuming the null hypothesis is true, since the p-value is less than alpha, we reject HO. So the first thing is to reject or fail to reject. We reject HO. We have sufficient evidence that those who receive the new procedure would have less recovery time than those who receive the standard. And that's how we do this. So take your time. This is a very unusual T, but it's correct. Make sure you know the notation. If this is greater than, then this should be greater than. Okay, they should match. These signs should match. And remind yourselves that you have to plug in these values. I didn't want to flip through the pages just to write them in, but you guys should write in all your values, okay? And that's how you do a 2-sample T. Leave a comment if you have any questions.